that's the first one, the time limitation. The second one is when you build all your design variations and now you start solving those designs, there are some limitation again in time and also in licensing. So at the given location, at the given company, you might not have enough licenses to run all the designs at one time. So you're going to have to do them in series. And this essentially, you have to babysit the simulation. You have to make sure that you're not running into any design errors and so on. So all this is being said because I want to show you how we can leverage the tools that we already have within the Siemens portfolio to optimize the variation and to optimize the optimization and to address what we call the intelligent design exploration. So with that, let me jump into the tool quickly. As you can see my screen, this is the machine that we're working on. This is the baseline machine. This is the design that we're going to optimize to minimize the magnet volume while maintaining the performance. So let's address the key features of the design. One of them being the winding. So usually the winding is developed in-house or it's part of the design. And the key features is you're trying to come up with innovative design, winding designs to minimize the winding factor, to minimize the harmonics, to address certain balance issues, to different types of techniques when designing the winding diagram. Once you have that set, the next step would be, of course, is to set up make sure that your design is working, make sure that you have, excuse me, your resistance is calculated and making sure the results. So let's start by just building a quick set of results and overview our design. So looking at the results, we can see that the machine is operating in the motor mode at 3000 RPM, generating 204 Newton meter with about 65 kilowatt power at a 94% efficiency. And the thing to note here is that we also have a measurement for the magnet volume used in the magnets. So how can we set up the optimization? And again, we're going to leverage the tools that are already available within the portfolio, within this tool, which is called Speed. We're going to leverage heats within Speed. To set up the problem, it's extremely easy. You have to set up your input parameters, which we leverage the fact that Speed is being analytical. You have access to all the design parameters. All you have to do is simply select the parameter from the drop-down list that you would like to optimize, or you'd like the optimizer to change and vary. Once you select it, you select the minimum and maximum values where you'd like the parameter to change in, and the resolution of the change. So how many data points between the minimum and maximum you'd like to select. And also, it's important to highlight how many maximum iterations we're doing. So for this specific case, we're not testing 5, we're not testing 15, we're testing 1,500 designs, changing 8 parameters in the rotor geometry to minimize the magnets while maintaining the performance. So those are the input parameters that we're using. There are 8 input parameters used on the rotor geometry to minimize, to essentially minimize the cogging torque, as well as to apply some constraints. The constraint applying to the optimizer in this case, the shaft power should not drop below 64 kilowatt. The back EMF should fall between 120 volts and 135 volts, because if we're reducing the magnet volume, we have to make sure that we're still operating in the range for the electrical drive connected to the machine. And at the same time, if we reduce the magnets to the point where we're still maintaining the performance, we are putting ourselves at a higher risk for demagnetization, because with the magnets being thinner than they should be, we risk magnetization. So once setting those designs together and setting all the inputs, all you have to do is run the study, and I have the results already from this. So let's run the analysis and see the results. So you can see that we've tested 1,500 designs with 4 error designs, and the design sets are broken into 3 sets: infeasible designs, feasible designs, and error designs. And the idea here is that whenever the optimizer generates a design that violates one of the constraints it classifies that design as an infeasible design. And whenever it generates a configuration that for some reason doesn't make sense from an electromagnetic standpoint, why other could be the tooth width too small, or for the changes that we made here, the magnet arc is too small or too big to fit in the rotor. So those are labeled as error designs. So whenever the optimizer encounters an error design, it doesn't stop the process. It simply labels it as an error designs and go to check the other designs. So based on this process, we end up with 637 feasible designs out of the 1,500 designs. And if we look at those designs, we have a huge list of all the designs that we label them as feasible designs. And if we do a simple sorting by the user variable, in this case, which is the magnet volume, we can see that we already have promising results while maintaining. For example, if we take a look at the top 5 designs, we're reducing the magnet volume, maintaining the shaft, and also reducing the cogging torque. And it also gives us the settings for those designs that generated the design. And the good thing is, if we look at the design, we can show the model of the design that gave us that specific, the best design, of course, the one that we select. And again, this tool is directly accessible from within Speed as the designer, and you can test. It only requires one license, so you don't have to worry about licensing issues. You don't have to worry about babysitting the simulation. It will automatically classify the designs based on the constraints that you give it and the objective functions that you specify for the optimizer. So again, let's go back and jump to the presentation and take into account the top 5 designs that we built. So moving on, this is a summary of what we did essentially. We have 8 rotor geometrical parameters. If you look at the design of the rotor, you can see on the top right corner, and we're changing all the design parameters that control the shape of the rotor to minimize the magnet volume. We're subjugating the constraint to the objective function to 3 constraints: the shaft power, the back EMF, and the magnet volume, of course. And with as I mentioned, we're considering 1,500 design iterations. With that,